Hello everyone. For this tutorial video, I would like to begin explaining how capacitors work, starting with a simple explanation of what capacitance actually is. As we should already know by now, a voltage is required throughout the whole circuit in order for electricity to flow. Although the exact amount of voltage does not matter, it just has to exist in general. But what I have not discussed up until this point, which will be important for capacitors, is that voltages, electrostatic forces, etc., act as fields across a distance rather than through direct contact, which is probably not already obvious from when you see an open circuit, for example, because there appears to be no voltage because there's no current. But evidence of voltage being a field force is in the fact that static electricity causes objects to repel each other without actually touching. And even in non-electrical contexts, you should be well aware of what a field force is already, because gravity is an everyday field force you feel, as gravity never involves objects touching to actually work. So now that we have explained how a field force is and given evidence that voltage is actually over a field, we can give more exact quantities related to field forces, which are important in the design of capacitors, which is field force, which is the strength or magnitude of the force, and field flux, which is the amount of force in total, regardless of magnitude. And field force and flux can be thought of as analogous to voltage and current in a normal circuit. Although the twist is that because fields act at a distance, they can exist within empty space as well, whereas electrical circuits always have to have a closed path to travel along. And it is also important to notice that different materials will conduct fields better than other materials, which is analogous to resistance of a normal circuit. So a capacitor is manufactured to take advantage of all of this by putting two conductive materials, usually made out of metal plates, separated by an insulator. And the modern schematic you will see for capacitors looks like this, which is a reference to how capacitors are commonly designed, as mentioned just now. And we should guess, based off what we know about how static electricity works, that when a voltage creates an electric field, excessive amounts of electrons gather on the negative side of the capacitor, while the positive side of the capacitor loses these electrons. And so the capacitor stores these electrons as energy. It should also be relatively obvious that the more electrons flowing through a capacitor, the stronger the field flux, which translates into a greater amount of energy stored. So because of how a capacitor is designed, it will resist changes in its voltage, which makes it behave in a much more complicated manner than simple resistors. And this also implies something that makes capacitors dangerous, which is that, unlike a resistor which has no voltage or current when it is outside the circuit, a capacitor can store voltage indefinitely, at least theoretically, so it can discharge energy quickly if it is given the right materials, such as a wet fingertip. One last thing to note before I give an exact formula to measure capacitance in, is that the older term for a capacitor is a condenser, because of how it condenses electrical energy into a particular point. Although most of the time you will hear people call it a capacitor, and condenser has mostly fallen out of fashion. But it is important to know that term too, because you will hear, for example, condenser mic, which means a microphone that uses a capacitor to store the energy rather than a magnetic coil. Now that I've explained the basics of how capacitors work, I can explain factors of how to predict exactly how much capacitance something will have in my next tutorial video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.